Hi, my name is Joonas, and I'm here today to talk about my favorite topic, Game Boys. I'm sure many of you recognize this little device. It's an original Game Boy from 1989. And this little device started a handheld game console family that was very popular. Even today, if you think about Nintendo's handheld console line like DS consoles, they don't have Game Boy in the name anymore, but they are definitely descendants of this device. So, the Game Boy console family started by this device. In total, there were 11 models released. One way to categorize these models is to split them into three hardware platform categories. One is the original Game Boy hardware platform that contained, well, the original hardware, the original instruction set. Many people think that Game Boy used Z80, but this is actually not true. The Game Boy used a custom 8-bit processor that is in many ways similar to Z80 and also similar to 8080, but it's not either one of those. Okay, so after the first hardware platform, we got the Game Boy Color, which was more like an incremental upgrade. We got color, and also some hardware features, quite minor things. And Game Boy Color platform can be backwards compatible. So Game Boy Color devices can run original Game Boy games, and also Game Boy Color games can choose whether they are only for Game Boy Color consoles or if they work on the original Game Boy as well. Then there's Game Boy Advance as well, which is a completely separate thing, completely new platform, instruction set architecture based on ARM. And Game Boy Advance games are not backwards compatible in any way. You can't put a Game Boy Advance game into an old Game Boy. So, Game Boys in 2018, are they still relevant? They are still very popular among emulator developers. So, it's quite typical that somebody who wants to get into emulation goes to some internet forum and asks, which platform should I emulate? Usually people say first that, okay, do chip 8. That's the easiest one. But what after that? Many people recommend the Game Boy. And yeah, if you go to GitHub, there's a lot of Game Boy emulators. There's also an active homebrew and modding scene. So even last year, there were some Game Boy game releases. And I'm not talking about just random ROMs on the internet, but like physical cartridges that you could order. The modding scene is also very active, so these original Game Boys didn't have any kind of backlight in the screen. So adding a backlight, that's a very cool thing to do. So in 30 years, a lot of hardware research has been done. I think we had the first Game Boy emulators in the late 90s or something like that. And after that, even more accurate emulators have been developed. So the hardware details are quite well understood. So I said quite well. We can ask, do we have a complete understanding of the Game Boy hardware? This question can be also rephrased in some different ways. Can we build an emulator that behaves just like real hardware? Or can we build an emulator which cannot be detected with a test ROM? So that, yeah, a Game Boy program couldn't detect that it's running in an emulator. And the answer is no, we can't build an emulator like this, at least not with public documentation. So, Mooneye GB, it's my Game Boy emulator. It doesn't support Game Boy Color games or Game Boy Advance games, but I'm focusing just on the original hardware platform at this point. In 2014, I wanted to get into emulation in some way, and I've owned a Game Boy Pocket since 1997, so I thought, yeah, why not do Game Boy? It's supposed to be easy. But eventually I found that the documentation was lacking. And I had more questions than answers. So I shifted my focus to hardware research. And today, Mooneye GB has very difficult but detailed hardware tests. And all this is based on real hardware research and validation. So I don't trust any documentation just because it's been available for a long time. And right now, there is no emulator that passes all of my tests. Yes, they work on real hardware, but no emulators can pass that. Okay, some people think that you can run Pokemon, so what's the point? Well, I think all official games should be runnable, even maybe unofficial ones. Yeah, like homebrew games, we really would like to run homebrew things in emulators. And not just the existing ones, but also to support homebrew development. So if you've spent 100 hours on some nice homebrew game, and then you find out that on one specific Game Boy Color version, real hardware, it just crashes completely. That's quite annoying if the emulator hasn't given you any help finding these kind of problems. Then there's speedrunners who care about accuracy. Pokemon speedrunning is a really serious thing. And preservation also. There will be a day when all the hardware will stop working, and we would like to understand the hardware better. This kind of research, very deep research, is difficult, but for me, at least, it's fun. That's also a very important reason. And one thing I like about the Game Boy is that I can imagine like a 100% completion for my research. It's not necessarily an infinite project. Okay, here's a very typical case example about emulator versus real hardware. Pinball Deluxe, a nice, simple, original Game Boy game. But if you run it in most emulators today, you see the result on the left. So after the game starts, it just crashes after a while, and that's it. On real hardware, it of course works. It's an officially released game. If it works on real hardware, yeah, they don't care if there's some edge cases that the emulators can't emulate. So just very quickly, here's Game Boy models. You can see that there's a lot of handheld devices, but also there's Super Game Boy and Super Game Boy 2, which are meant for Super Nintendo. So you can play Game Boy games by using these on a Super Nintendo and a TV. And also there's the Game Boy Player, third one from the bottom left, that can be used to play Game Boy games on GameCube. All right, so a bit more technical stuff then. Game Boy CPU chips. One nice thing about the Game Boy is that the central CPU chip handles pretty much everything. So instead of like early Super Nintendo versions where you had the CPU, you had the pixel processing unit 1 and pixel processing unit 2, all separate chips, on Game Boy it's one chip. It's basically a system on a chip. And if we just focus on the original Game Boy and Game Boy Color platforms, it's same instruction set in all the models, and the same basic hardware is the same. So we can make this kind of assumption that the behavior of the system depends on just this one chip. So just by looking at this one chip, we should be able to figure out the behavior behind the entire system. This is not completely true. There's some cases, some things that can also affect behavior in theory. So there's mainboard versions and individual unit differences. And this might affect things because there's things like analog behavior. Many people think that the original Game Boy had the best bass, the boomiest bass. So I'm not sure it's about the CPU chip. I think it might be the supporting chips that affect this. There's also like semi-random behavior, static RAM initial values. They are not truly random. More like certain bits tend to be ones and certain tend to be zeros. But yeah, it's not really deterministic. But we'll just ignore this, and that's a very nice assumption to have. Okay, I like to divide the CPUs into generations. They are QFP chips, and if you look at the pinout, you can group these different CPU versions. So there's like 5 generations. Later generations add a bit more pins and so on. And actually, there's a generation 6 as well, but that uses a BGA chip. And this particular chip is not backwards compatible, so I'll just ignore that. Okay, so let's say you build an emulator and you use x16 documentation. Which CPU version are you actually emulating? Is it the original Game Boy CPU? Or the next one that has a bit different silk screen? Or the A? Or the B? Or the globtop version? Or the C? Or the SGB? Or the MGB, SGB2? Or Game Boy Color chips? Is it one of these? Or Game Boy Advance chips? And yeah, the last one is the BGA chip, so we'll just ignore that. So in total, we have around 20 versions, depending on what you assume that, for example, the two chips that have slightly different labels, are they the same chip or not? Okay, around 20 versions. Now, and just to illustrate that this matters in some edge cases, there's a very popular audio test ROM. It's a very good test ROM, but if you run it on the first and second generation CPUs, it works on the first one, it doesn't work on the second one, then it works for the next 3 versions, and then it stops working for the next 3. So if you're basing your emulator on this audio test ROM, which chip are you emulating? And we can also ask, which version should we emulate? What's the best one? Is it the most popular one, or the latest version with, of course, all the hardware bugs fixed? And real hardware has backwards compatibility issues as well. So this is an example with the Game Boy Color. So there's a game called Donkey Kong Land 3. And if you run it on Game Boy Color or later devices, the sprites have these weird horizontal glitch lines. There's a timing difference in Game Boy Color and earlier devices, so you can't run this without glitches, except on the old hardware. And a proper emulator would also emulate these glitches, because otherwise you would not be emulating Game Boy Color if that's your target. Okay, so the solution is just research everything. So here's a photo with most of my Game Boys. And so I showed you all the CPU versions. Only one of them is missing. And all Moon GB tests are verified on all hardware versions I own. So every time I write a new test, I test it 19 times. And I would like to test it 20 times if I had the last CPU. Okay, let's move on to some hardware research tools. How do I find information about the Game Boy? The first thing is that I can use a flashcard and some test ROMs. So here's 2 flashcards. The first one has a USB connection, so you just plug a cable there, flash the ROM, take the cable out, and run it on a real hardware. That's nice. But the annoying thing is that you can't keep the cable connected. So then I designed my own PCB, my own flashcard, the GB Live 32, which also has a USB connection, but you just keep it plugged in all the time. With one command from some random bash script or something, you can just flash it and reboot the system. No cable, you don't need to detach any cables. So that's nice. We could also probe the CPU, solder some stuff to CPU pins. And for this purpose, I also have some custom boards. I've got these breakout boards, the M and F. And together, you can have this kind of pass-through where you can have a real cartridge connected to a real device and have access to all the 32 cartridge bus pins. So that's quite nice. On the right, you see a Super Famicom, so a Japanese Super Nintendo basically, a Super Game Boy, these 2 breakout cards, a logic analyzer, a lot of wires, and a dock. Never forget the dock. Another option is to just desolder the CPU and put it on some custom test board. So I also have a board for this, a custom board. So this one, GB Bench G1, it's a custom test board for first generation Game Boy CPUs. And yeah, a custom 4-layer PCB. There's a complete first generation Game Boy on the board. So it has the CPU, the RAM chips, the cartridge connector. It doesn't have a joypad, an LCD, or a speaker, but all the signals are there. It's completely functional. In addition to that, I also have 2 lattice CPLDs that give me full bidirectional access to all the CPU pins, all the digital pins at least. And this board alone doesn't do much. It needs a control board that connects with a parallel control bus. So I've got a TNC 3.6 controller board as well. And on the software side, I've got these automated tests written with Lisp. So I can just test this entire system quite easily. And because I see all the signals that are in the CPU pins, I can capture a CSV file, a value change dump file. And because the LCD signals are there, I can capture a PNG, just all the frames that would be seen on the Game Boy. And this is all possible to do in an automated way. All right, so let's do a demo. Okay, so I've got the main GB Bench board here, and then there's the controller board with a Teensy on top. And I've got two games here. I've got the original Tetris. Let's start with that one. So I'm just going to connect the Tetris game to the board. And then I've got this Lisp test that basically does a sequence of steps. First of all, we reset the system. We let the CPU run until it's ready to execute the first instruction of the ROM. Then we spawn some writers. We want to collect some data. And finally, we arm some triggers. This is basically just a way to sort of quickly wait until certain signals are visible. So I know that Tetris is almost ready to go to the title screen when this address is being read. So I'm just going to arm a trigger there and wait at most 20 seconds. And then we step 400,000 clock edges of full hardware samples. All right. This will take a while. One of the annoying things about Tetris is that it takes forever to get to the title screen. We should be, yeah, okay. We see that some lights are blinking. It's aligned to the title screen and collecting the 400,000 samples. All right, we're done. And now we can take a look. Yeah, there's some signals there. All right, the raw signals are a bit boring, so let's do something different. I've got this nice Python script that looks at the CSV file that was just collected, and it extracts from the raw LCD signals the frames. So it found two frames that were identical. And what's the frame? Oh, it's Tetris. And let's just do quickly another one. We've got the Super Mario Land. And for this one I have a different trigger point. And that's it. So let's run the Python script again. And we've got Super Mario Land. And there was another frame with the mushroom sprite. Yeah. That's how it works. OK, so I can use existing cartridges and test them. But one of the important things about this board is also that I can create and run automated tests that just don't use any ROM. Because I've got control of all the signals. I can pretend to be ROM. And I've got this test set of low-level hardware tests. It's just running stuff there. And this verifies my understanding of the Game Boy. All tests passed. Yes. And I can also run the same test set on a different version, a different CPU. I just need a different board. I've got 3 of these, so yeah. All right, that's it for the demo. Let's go back to the hardware research tools and methods. One way to find information about a CPU chip is to decap it. So this photo is from the Silicon Pron website. We only have, at the moment, a photo of the top layer. So it's not possible to reverse engineer the entire transistor structure in detail. You might have heard of Visual 6502. That's a project that did a full reverse engineering based on these kind of photos. But yeah, we only have the top layer. But even with the top layer, we can see how things are connected. And maybe we can gain some information from that. OK, so here's the chip. Let's fade it a bit so we can highlight things a bit easier. Add all the pin labels. There's quite a lot of pins there. Well, technically, these are bonding pads, which in the package actually have tiny wires going to the pins. Let's add the supply nets. So we've got the ground and the power. and they form this kind of rectangle around the chip. And then just add all the pins. So we see where things are connected. And, well, I've also done a bit more. So if we also add some internal signals, yeah, that's quite a lot of stuff. Now, it's a mess. There's a huge amount of signals and stuff. It might be better to just focus on some of them. For example, we can just see where the video RAM address pins go and the LCD pins. And all these go to the bottom left corner of the device into this big pile of logic and transistors. So that's most likely the PPU. The PPU is on the same chip, and the PPU cares about these signals. Another thing we can see is if we highlight all the data pins and at least some of the control pins. And those things go to the top left and also to the top middle in a bit bigger area. So these areas are most likely some kind of bus control timing related things. So just by looking at how things are connected, we can make some guesses. Okay. We can also see that this area here contains some kind of mask ROM. And I know that it's the boot ROM. This chip doesn't really have any other big ROMs. And if we zoom in a bit, this is what the boot ROM looks like. And you can see those tiny white dots. Those are the individual bits in the boot ROM. And one way to dump the boot ROM is to read out the bits. I don't actually know what the pattern is. It's not the kind of obvious left to right, top down. But yeah, it's possible. Now, speaking of boot ROM, let's talk about it a bit more. The boot ROM is the piece of code that executes when the Game Boy starts. And it's responsible for the scrolling Nintendo logo that you might know. Boot ROMs have been dumped quite a lot. There's several versions. The first one was dumped in 2003, and that was done with visual inspection. I've dumped 2 boot ROMs that were previously not dumped at all. So the CPU starts from address 0 after reset. After reset, the boot ROM is mapped to the first 256 bytes in the address space. The external ROM is mapped to the first half of the address space, so there's overlap. But the boot ROM always has priority when it's enabled. So basically, when the CPU starts executing instructions, it's going to execute the boot ROM, and the external ROM doesn't get any chance to execute anything until the boot ROM has done its things. And the last boot ROM instruction actually unmaps the boot ROM. So when we have control, the boot ROM is not readable anymore. It's gone. Too late. So we need a way to stop the unmapping, prevent the boot ROM from basically killing itself. So what kind of attack vectors could we have for this kind of dumping? Well, we can't really use flashcards and test ROMs because, like I said, the external ROM doesn't get any control until it's too late. We could do some stuff with probes and solder some stuff. Yeah, there's some ways to dump it. We could also use a test board where we have control of all the pins. There's a slightly different technique for that, but my board can also dump the boot ROM. And yes, we can use some visual methods to, we can decap and inspect the entire CPU and read out the boot ROM. Okay, so time for another demo. So I'm going to dump the boot ROM, and I'm going to use this clock glitching method, which I believe was first discovered by Ben Venn. And this requires no soldering. All I need is one wire. And, well, a flash card that has a special boot dumper ROM. So the dumper ROM basically just copies the first 256 bytes to the cartridge save RAM. So we can then access it from the computer. All right. Where's the wire? All right. Let's see how this goes. So first, I'm just going to start the Game Boy without doing anything, not using the one wire. So we see Nintendo logo scrolling. And there's a sad face. The dumper program didn't detect the boot ROM. OK. Yeah. I didn't do anything special, so it's obvious that, yeah, the boot ROM killed itself and it's gone. But this time, I might need to try this a couple of times. I've got a couple of seconds while the Nintendo logo is scrolling to put this wire into some places. So one end of the wire is going to ground connection, and with the other end, I'm just going to gently scratch one of the clock pins. And this should glitch the clock so that it jumps somewhere. And the dumper ROM basically has a lot of knobs and a jump in the end, so if the CPU happens to jump into some place controlled by me, it will end up in the main dumper program. All right, let's see. Nope. Oh, happy face. So now we have a copy of the boot ROM on the cartridge save RAM. I'm not going to verify it. That takes time, but yeah, it works, trust me. All you need is one wire. OK, that's it for the demo. Let's continue. So the title of my talk promised some fine details. So I'm going to give you some fine details about instruction decoding and interrupts on the Game Boy. This will be technical and very quick part of the presentation, but yeah. Some of the information I'm presenting here, you can't find it on any public documentation, even my own documentation, because I'm not sure about some of this yet. OK, so we have this Game Boy program that consists of 3 instructions. We have a NOP instruction that does nothing. Then we have a load instruction to a certain memory address that just copies the value of the accumulator to that address. And finally, we have increment accumulator instruction. And the first instruction starts from address 1234 in hex. And the actual data byte is 00, that's an op on Game Boy. And the second instruction actually consists of 3 bytes, because there's the opcode and 2 bytes for the address. And the last instruction is another 1-byte instruction. OK. Some basics about instruction timing on Game Boy first. Instructions always have a duration of the duration of instructions is always a multiple of 4 clock cycles. And we call this 4 clock cycle, like chunk, a machine cycle. And a good rule of thumb is that a machine cycle is required for each memory access. So by looking at an instruction and thinking about it, how many memory reads does it do? How many memory writes does it do? You can have a pretty good guess how long the instruction is in machine cycles. An example is pop BC, which pops a 16-bit value from the stack and puts it in the BC register pair. So first of all, we have the opcode read, the opcode itself. Then we need to pop the low byte and copy it to C, register C. That's another memory read. And also we pop the high byte, and that goes to register B. So 3 machine cycles. Simple. So it's a good rule of thumb. It's not always correct, but most of the time, this is how it goes. OK. Let's go back to the program we had. And now we need to take a look at some timing diagrams. We know that the system has around 4 megahertz clock signal. And if we look at all the CPU pins, and well, actually just the cartridge bus pins, we find that there's another clock signal there that is 1 megahertz signal, 1 megahertz clock signal. So machine cycles where machine cycles were 4 clock cycles each. So this looks like maybe this 1 megahertz clock is a machine cycle clock. Yeah, would make sense. We also can see some addresses on the address bus. We see each address for each of the individual bytes in the program, and also the target address that we are going to write in the load instruction. If we look at the data bus, we see, once again, all the data that correspond to the bytes in the instructions. And also we see the value of A, whatever that is, during the write cycle. Then we also have some control signals. These are all active low signals. So for example, read is active most of the time, and it goes high just for a bit when the write happens. The chip select, actually there's multiple chip select signals, but it depends on which device you are accessing. But there's a chip select signal, and that pulses low in each of the machine cycles. where we need to access this device, which is now an external ROM, basically. And finally, we have the write signal, which is high most of the time, but it goes low in the end of the write machine cycle. OK, this seems quite simple, and yeah. And we can then just have a lucky guess that maybe the instruction boundaries, so where the instructions start and end, could be like something like this. That would align with the 1 megahertz clock. Yeah, would make sense. Now, if we run this program on the test bench, and we are pretending to be a ROM, we don't actually have to care about the chip select. We can just have rubbish data on the bus all the time, except for that one clock edge when the Game Boy actually cares about the data bus. And if we do this, we find out that there's just one clock edge in the middle where the data bus contents matter. OK, so we've identified the clock edge where this data bus is sampled. Simple. Now, we don't want to actually stop here, because there's another way to investigate how the Game Boy executes instructions. We can abuse serial I/O a bit. There's 2 pins on the CPU that we care about. There's a clock pin and an input pin for the serial. There's 2 registers. There's a control register and a byte register. And the control register, we can use that to start a serial transfer and also choose which side of the serial connection is the master that controls the clock. And because we are using a test bench, of course, we want to be the master. So we'll just have the Game Boy in a slave mode. And that means that when we pulse the clock pin, we can feed in bits to the serial byte register, which is basically just a simple shift register. So by having control of these 2 pins and starting this kind of transfer, we can just choose the value of SB, basically. And one thing about the serial I/O is that it's completely asynchronous to the main clock. We can stop the Game Boy clock. We can shift in 7 bits if we want, and then continue with the clock, and the Game Boy sees a modified SB value. And this gives us a lot of control and possibilities to do things. So in order to see when data is sampled, let's first set up a serial transfer and then jump to SB. The Game Boy doesn't care where the instructions are. You can jump to any address. Jumping into hardware registers is my favorite, because you can do a lot of things with that. And by controlling the value of SB, we can then see what instruction was actually executed. OK, so this is a simple diagram showing this case. So we see that the Game Boy is reading the SB address. And in this case, where the SB has an initial value of FF, and we are not modifying it, the corresponding instruction for FF is RST38, which is just a quick function call to address 38. And I also have the vertical line in the diagram. That was the point of time, the clock edge, where the sampling happened in the previous example. OK, so now that we have control of SB, we can choose at some point of time where we change the value. So what if we just feed zeros, 8 0 bits to SB right before this sampling edge? OK, well then the Game Boy actually executes a NOP, which is 0, 0. So we've changed what instruction it executes even after the instruction read has started. OK, simple. We can also move the time a bit. So let's add 1 cycle. OK, but now we are past the edge, clock edge where we thought sampling happened, and it didn't. So clearly, the sampling edge is wrong, because at that point, it would have seen FF, but it executed NOP. OK, we can keep doing this, and eventually we find that the last point when we can feed 0, 0 and have the Game Boy execute 0, 0 is at that point. And this is a bit weird, because that clock edge, based on our instruction boundaries that we have in the diagram, is supposed to be the first clock edge of the next opcode. So this maybe something wrong here. So looking at the original program, what we had was this. The sampling happened basically in the falling edge of the machine clock. But the reality actually is something like this. OK, so it's a bit weird that the first rising edge would be of the next instruction would be the time when the previous instruction is actually executed. OK, and we can shift our guess about where the instruction starts and stops, and because that's just something we use to understand the system. Everything else is real signals, but the instruction boundaries are something that we just made up. So this is an open question still. Where does the instruction start and where does it end? We see all the signals, but what's the beginning? OK, so maybe it's wrong machine cycle boundaries. Maybe there's some pipelining. Even the 6502, a very popular processor as well, had a very simple pipelining, as far as I know, where the fetch of the next instruction overlaps the execution of the current instruction. So this would also explain things. But it's an open question. OK, another example. This is the last thing. Interrupt handling. Interrupts are only checked between instructions. Otherwise, you could have an interrupt in the middle of an instruction that does multiple things, and you would only see some side effects. For example, you push a 16-bit value, you would only see the 8-bit, the first push. That wouldn't make any sense. So interrupts like retain the instruction boundaries. Interrupt handling takes 5 machine cycles on Game Boy. This is testable with some test ROMs, and you can find this in some documentation. There's 5 possible interrupt sources that can cause interrupts, and they have a priority. If 2 interrupts happen, and then the interrupts are checked after some instruction, only the highest priority interrupt is actually handled. OK, so more timing diagrams. This time we are just executing in knobs to keep it simple. So if the interrupts are checked between instructions, we would assume that those red vertical lines would be the points where the interrupts are checked. So if an interrupt happened in this blue line, we would expect all the knobs to be ignored. And instead, we have interrupt dispatching, so the 5 machine cycles. And after that, we have the first instruction of the actual interrupt handler, the code. OK, this is what we would expect. Now, to study interrupts, we can once again abuse serial I/O, because serial transfers are one of the interrupt sources. So because the serial I/O is asynchronous in this case, we can just trigger 8 clock pulses to trigger an interrupt at any point we want. Between clock edges, we can stop the time of the Game Boy and just feed an interrupt anywhere. So if we do that, we actually find that it's more like this. So there was like a 2 clock cycle offset. So now if an interrupt happens where the blue line is, then we get interrupt dispatch. And if it happens 1 clock edge later, it doesn't do this interrupt dispatching. OK, this doesn't quite match what we would have expected. This also means that the Game Boy CPU starts reading stuff, and then it decides much later if it wants to actually sample the data or not. So it basically just cancels the read and starts doing interrupts instead. OK, there's another clock edge that's meaningful. So it turns out that the first clock edge, the red line, is just a check, should we do some interrupt dispatching? But when the Game Boy chooses which interrupt to serve, that happens at a different time. And that's the second clock edge, the red line. So now there's a blue line and an orange line. If a low priority interrupt triggered the interrupt dispatch at the blue line, and another high priority interrupt happened at the orange line, it would not serve the low priority interrupt at all. It would just do the high priority. So there's a conflict. Okay. So interrupts are checked at the falling machine clock edge, which is not what you would expect based on the information we have. And the address where we are jumping is checked much later. So the different times for should we jump and where to jump. And a higher priority interrupt can completely take over. And I don't know if you remember Pinball Deluxe. That was I showed some screens from that game. Changing emulators to match this behavior was one of the keys to almost fixing Pinball Deluxe. It doesn't work yet on my emulator, but there's one emulator called Sameboy that emulates Pinball Deluxe today correctly after making changes based on these findings. Okay, final words. So even after 30 years, there's still work. We still have open questions. I showed you all these different CPU versions, but I didn't explain any differences because I just don't know. It's still unclear. And for me, it's really fun to do this kind of very deep hardware research, reverse engineering and research. And even very core concepts that you would think that we would understand now, like instruction execution and interrupt handling, we would understand this, but they still have surprises. All right, that's all. There's a couple of links for many Game Boy things I've done. I think we have some time for questions, if there are any. All right, if you have any questions later, just find me, and yeah, I'm happy to chat about Game Boys. Thank you.